Let us start the lecture. So we already have some discussion about different sensor parameters. So I'll just quickly recap those parameters. So we have seen in the last lecture what is a threshold, and we now know that threshold is the minimum input that is needed for the sensor to work. What I mean by that is, if you have a temperature sensor and if someone says that the threshold of this sensor is 2 degrees centigrade, then it means that at least 2 degrees centigrade temperature is needed for this sensor to work. The sensor cannot work below 2 degrees centigrade. Okay, and then we have discussed what is an offset. So offset is a term where you get an output when you don't have an input. So just briefly again saying, if you have a sensor where even when your input is 0, if you get certain output, then this particular output is known as offset. Okay, so one has to be very careful while working with sensors, because a few sensors may have offset when you begin with that sensor for certain application. Even when you have offset in a sensor, you can work with it, but you have to make sure when you start your operation the offset is set to 0. Usually this is the approach. Apart from that, offset may also come into your sensor system because of linearization, as we have seen in the previous lecture. Once you linearize the calibration curve, due to that linearization process, you may end up with getting an offset in that. But again, you can work with it, but you have to take care of that offset properly, otherwise things may not work as you wish. Secondly, it's not a property completely associated with sensor. This also can be associated with system. So offset can come in your entire sensor system because of the circuits that is there in the system. Okay, many of the sensor parameters that we are currently discussing also is applicable to system. Okay, a system can also malfunction, and then your entire performance of the sensor system may get disturbed. Sensor system means the sensor when it is connected with a system. Okay, so this is sensor and then this is system. So the entire thing is sensor system. For example, if you have a digital thermometer, it has a temperature sensor. Say if this is the digital thermometer, the temperature sensor is placed at the top of that thermometer usually, and then it is connected to a circuit, then it has a display. So the entire thing is a sensor system. So if sensor is working well but your system is not working properly, then anyways you will get a wrong result. So you have to be very careful not only about the sensor but also about the system. Then we have discussed about range. Range is nothing but in the window that you take for sensor operation. If it is temperature, and if your temperature if your sensor response is useful in certain range of temperature, say from 20 degrees centigrade to 100 degrees centigrade, then this 20 to 100 is your range. Okay, so that is how you define a range. As we have said in the previous class also, range doesn't mean that the sensor will not give you an output beyond that. There are cases where beyond range probably the sensor will get damaged or it's not stable, but there are also cases where beyond the range also the sensor will have some output, but it will not follow the same calibration curve or the way you have maybe designed the system. Okay, what I mean by that is, after that range maybe the sensor response is something else. Below that 20 degrees centigrade, maybe the sensor response is something else, something like that. Okay, but you are operating only in this zone. You have to be very clear about the range of that sensor. Then we have seen linearity and non-linearity. We usually try to have higher linearity, and that actually helps us in system design. Then we have seen hysteresis. The target is to have low hysteresis so that we can work with that sensor smoothly. I already have said, even if you have hysteresis, you can work with that sensor, but usually we want as low as possible. The hysteresis should be as low as possible. Okay, ideally it should be 0, but anyways, even if you have it, it should be as low as possible. If it is very high, then you need to think of something else if you want to use that sensor in your application. And then we also said that there are certain applications where probably hysteresis is needed. Then it's a separate issue altogether. Sometimes you use the drawback of your system as a major parameter for certain application. Okay, that is what engineering is all about. So that is how we also design sometimes the sensors. So today we will discuss about a term called selectivity. From the name itself, it is very clear. Selectivity is the property which shows how selective your sensor is towards the stimulus. What I mean by that is, this particular term is more kind of applicable for chemical sensors and biosensors. For example, say you have developed a biosensor which detects say blood glucose or blood amylase. Now the sensor that you have developed is electronic sensor, of course. That sensor also should have a mechanism through which the sensor can only detect blood glucose or blood amylase. Let us take an example of blood glucose. So you have a sensor and you want to detect, say, glucose in human blood. So the sensor must react only with glucose present in the blood and provide you certain output. Let me first tell you briefly how chemical sensors work. So chemical sensors or biosensors are based on reactions. So if you have a chemical sensor or biosensor, that particular biosensor should have certain chemical, we call it, let's call it A in this case. Okay, so if you have a chemical sensor, then you have a base material, say A, and this material will detect with, say, B, that is your biomarker. So once A and B reacts, it will produce certain sort of electron transfer or charge transfer in the sensor that will influence the electrical response in the output. So this is more or less briefly saying how chemical sensors work, one of the ways. Now if you put blood on this sensor, blood will have several other components, different proteins, RBCs, WBCs, etc. Now you have to make sure that these other components are not reacting with the material A. If A and B, that reaction is not very specific, then other materials present in blood may also react with them and give you a wrong signal. So your sensor selectivity will depend on the specificity of the reaction between A, that is the active material that you put in the sensor, and with B, that is the biomarker, in case it is glucose. So for that purpose, we take different reactions that we will discuss once we come to the chemical sensor part, but selectivity is defined in that way. So in case of biosensors and chemical sensors, your sensor should be very selective to the analyte under consideration. Otherwise you will get a lot of noise or maybe incorrect results. Then we also have another term called repeatability. Repeatability is again very important. So that is again, I mean, it's applicable to almost all the sensors, but again is very important for specifically biosensors and chemical sensors, because many a times you may find the sensor is not repeatable. Or even if you take an example of temperature sensor, say you have developed a temperature sensor, you are measuring temperature, but when you repeat that measurement, maybe the measurement is not coming correctly. So the repeatability is very less in this case. So repeatability again is a very important parameter that one has to look after when they develop or when we develop sensors. The other very important term is reproducibility. So reproducibility shows how reproducible results are. So if you have a sensor which detects, say again, blood glucose, you get a certain output, say A, for concentration, say C. But next time when you make another sensor and do the same experiment with concentration C, you don't get the output A, it's something else. In that case, your sensors are not reproducible. So there is a small difference between repeatability and reproducibility. Although they may sound very similar, but they are actually different. Repeatability is for the same sensor. If you use the same sensor again and again, how repeatable your response is. If it is a reusable sensor, there are also disposable sensors where you use the sensor once and then you throw it. In most of the biosensors application, disposable sensor is much better, because then the chances of contamination is much lower. However, in that case, you have to see the reproducibility. You make 10 different sensors and do the same experiment and see whether these sensors are giving same results for the same concentration of analyte or not. That is what I'm saying currently. So you have 5 different sensors, you have done the experiment for same concentration of blood glucose, and then you are getting, in one case A1, in other case A2, in other case A3, case A4, and all these A1, A2, A3, A4 are very different from each other, then it is not very reproducible. So for a sensor to be applicable in a certain application, you must ensure that the reproducibility is very high. Now, the repeatability that I have said can be measured from calibration curves. So how do you measure? For example, if you have an input, or if you make a sensor, say for temperature, what you do is you first measure the calibration curve for this particular sensor and say this is what you get. So what you have done, you have changed the temperature, because in this case it is temperature. You measured the output, you have now this plot. This is what your calibration curve is. Then what you have done, for the same sensor you have done the experiment again. You again changed the temperature, you measured the response, and you got a response or calibration curve which is like this, the second one, run 2. Now you can calculate the repeatability delta R with capital delta, which is the maximum difference that you get, divided by the full scale, that is from 0 to the 100% into 100. That will give you the percentage of repeatability. So this is an equation which you may use to check the repeatability of your system. However, in case of reproducibility, this is no longer the same sensor. So run 1 and run 2 is not applicable. Run 1 and run 2 is not applicable if it is a disposable sensor, right? So in that case, you have to see the reproducibility. Then we have a concept called deadband, which to some extent I have discussed previously. Deadband is a small portion in your entire range where the sensor is not sensitive. What I mean by that is, for example, if you have a calibration curve, something like that, so you can say use this sensor for this range again take an example of temperature sensor and consider this is 10 degrees centigrade. This probably you may consider as maybe 30 degrees centigrade. This is maybe 60 degrees centigrade, and this again is like say 80 degrees centigrade. Okay, now you can see that it has different sensitivities. From 10 to 30 it has one sensitivity, from 60 to 80 it has another sensitivity, but between 30 and 60 there is no sensitivity. The slope of this portion is almost 0 because it's parallel to the x-axis or input axis. So the sensitivity in this range is almost 0. That means the sensor is insensitive, and we can consider this part as deadband. So although the range of the sensor is from 10 to 80, but from 30 to 60 the sensor cannot be operated. So one has to figure out if there is any deadband in the entire in the entire range of that sensor or not. If there is a deadband, then you should explicitly mention that particular deadband of your sensor, because if someone uses your sensor in this range, then he or she will not get any output out of this sensor, because there is no change in output even if the input is changing. Okay, so this is what deadband is all about. Then we have a term called resolution. Resolution refers to the smallest increment of the input or stimulus that can be detected. So if you take again an example of temperature sensors, say you can detect temperatures like 10 degrees centigrade, then 15 degrees centigrade, 20 degrees centigrade, then the resolution here is 5 degrees centigrade, right? Because you cannot detect any temperature between 10 and 15. Say you have a sensor, I repeat, say you have a sensor which can detect 10 degree, 15 degree, 20 degree, 25 degree, and so on and so forth. But it cannot detect anything between 10 and 15. So in that case your resolution is 5 degree, because this is the minimum change delta T that it can detect. And you have another sensor, sensor B, which can detect 10 degrees centigrade, 11 degrees centigrade, 12 degrees centigrade, and so on and so forth. It cannot detect anything between 10 and 11. The minimum change it can detect is 1 degree centigrade. Then the resolution of this sensor is 1 degree centigrade. So the resolution in this case in sensor B, that is this one, is higher than sensor A, that is in this case. We will call the resolution in this case is higher because it can detect very small increment. So the resolution is higher in this case, because if you consider temperature between 10 degrees centigrade to 15 degrees centigrade, sensor B can detect 5 different values, high number of values for sensor A, and sensor B can detect 5 values, 1 degree change it can detect. So 10, 11, 12, 13, 14, 15. Between 10 and 15 it can detect around 5 different values if we leave that first value, okay, 10 degrees. So 11, 12, 13, 14, 15, 5 values. For sensor A it can detect only one value after 10. So this can detect more number of values, and we will consider sensor B to be, or the resolution of the sensor B to be high or higher than sensor A. Okay, so that is what the resolution is, and we usually target to have an high resolution sensor. Okay, then we have another term which is known as stability. So stability again is a very important parameter. Stability refers to the robustness of a sensor, how robust your sensor is. If your sensor is not well stable, then it's again a problem. So stability can be mechanical, electrical, chemical. So a sensor can be less stable mechanically, less stable electrically, less stable chemically if it's a chemical sensor, or any other sensor for that matter. So any type of stability, if it is low, then it will affect lot of other parameters as well. What I mean by that is, if your sensor is less stable mechanically, then anyways that instability that is there, mechanical instability that is there in the sensor will also influence the electrical response of it. For example, say you have a flexible sensor. Now if you bend the flexible sensor, the electrode breaks. So the mechanical stability of the electrodes of that flexible sensor is not very good. But if electrode breaks, then anyways you will get a poor electrical response. So mostly each of these stabilities are interlinked. You have to ensure that the sensor is stable in all possible way. So a certain amount of stability is needed. Now in case of wearable and flexible sensors, the stability study with bending condition is necessary analysis. In almost all wearable and flexible sensors, you will find people give that stability analysis, and the stability error can be defined using this. So it's delta is the stability error, and SD is the standard deviation of the data, and gamma is the mean. So if you find the standard deviation and mean of the data, you can define your stability of the system. So it's mostly the electrical stability that we are talking about. Okay, so this is again a very important parameter in most of the sensors. Then we have another very important parameter, which is noise. So noise is an unwanted signal or fluctuation in the output while measuring the stimulus or input or any parameter. So we usually try to avoid noise. There are many reasons why you'll see noise in your system. Again, noise is not only a parameter that is related to sensor, it is also equally related to your system. So your sensor can be noisy, or your system itself also can be noisy. If your system is noisy, then ultimately your output that you get will be noisy. If your sensor is noisy, then using a proper system you may suppress the noise in the sensor. Okay, so what are the different reasons that may create noise in your system or sensor? One of the major reason of noise is the environmental parameters or ambient condition. For example, if you have a temperature sensor, and if there is an material which is the active material of your sensor is also kind of influenced, or it can get influenced by relative humidity around it, then you'll see an unwanted signal because of the relative humidity change. So the active material is responsive towards any of the other ambient condition other than the parameter under interest. It may create a noise. Sometimes the noise also is due to system. For example, in the system you have some electrodes or you have some interconnection which are not properly made, then the contact resistance of that interconnection or the connection may create a noise in the system. There can be other noise like flicker noise and etc. that probably I'll discuss during the system description, if not in very details, but at least to some extent. So if there is some unwanted signal that is passing around the sensor, where you have sensor that you placed in a PCB, the influence of those PCB lines may create a noise in the system as well. What I mean by this is, for example, say your sensor is placed somewhere here in a PCB. PCB is printed circuit board. That is the board that you see usually inside a electronic gadget. Okay, so you placed your sensor somewhere in the middle of the PCB, and then there are multiple connections around that device, and those connections or those conductors also carry current, and when those currents are flowing through those conductors, they'll create certain sort of magnetic field. They sometimes create an capacitive effect because both the conductors are very close to each other. There is some dielectric, maybe say air in this case can act as a dielectric and will create some certain sort of capacitance, and that changes the entire performance of your system and changes the calibration curve, influence the calibration curve, and they may create a noise in your system. So that also can be a source of your noise. So when you are designing a system, for example, if it is a capacitive sensor, or let's take an antenna for that matter, for example, you are developing a wireless system where your sensor will be connected to the sensor circuit, and then it will be connected to an antenna, okay, which will transmit the signal to say a mobile application or something like that. Now when you develop an antenna, you must know what is the impedance of that antenna, okay, and then if the impedance is not matching with the circuit that you are using with this antenna, then definitely there will be a shift in frequency, resonant frequency, and you will find that a lot of noise is actually coming in the display device, okay. So these capacitance should be taken under consideration when you are connecting the sensors or antennas into the circuit. Otherwise this may end up with a noisy signal, okay. So one has to be very careful about different types of noises. Then if you want to work with a microfluidic sensor, say a droplet based sensor, say a droplet is kept and this droplet probably is capable of detecting something, okay. I'll give you some example later, or maybe I've given you already. So if you want to use the droplet as a sensor, then if there is certain sort of motion in the air around this droplet, you'll find that this motion influences the flow inside the droplet, and it in turn creates a noise in the output signal, okay. So you don't get a proper signal, rather you end up getting a noisy signal. So these are the sources of noises. There are different types of noises, and one should be very careful about the unwanted signals and noise in your sensor. So the three take home messages in this lecture are, first one is selectivity is very important, okay, for chemical and biosensors, because if the selectivity is poor, then definitely your sensor will provide an incorrect information. If you are targeting to detect glucose, your sensor should react with only glucose. It should not react with say albumin, creatinine, amylase or other enzymes or other proteins present in the blood, okay. So selectivity is very important for chemical and biosensors because most of them are chemical reaction based. Then environmental factor may reduce the reproducibility of a sensor, as I have said. If you have a temperature sensor and the active material of that sensor is responsive to relative humidity, then you will find the relative humidity of the environment or ambient condition is making your sensor less reproducible, okay. So one has to be very careful about that. Then most of the stability parameters are interlinked, that is, if one type of stability is not good, the other stability also will get influenced. So what I mean by that is, if you have a flexible sensor and if the sensor mechanical stability of the sensor is not good, that will be reflected in your electrical signal as well, because maybe the electrodes are not stable. Once you bend it, the electrodes are getting affected, so in turn you'll get an very bad electrical response, okay. So the question that I would like to ask is it possible to work with a noisy sensor? So I have said noise is something that we should avoid, but say you have a sensor which itself is very noisy. So can we use this sensor for certain application? This might be any type of sensor. You can take an example of say temperature or chemical or biosensor. The Question is, if you have a sensor which is noisy, then can we work with that sensor to some extent, or is it possible at all to work with that sensor? Let's think. Okay. In the next class, we will discuss few more sensor terminologies, because we still have a few more very important sensor terminologies left. If you don't have a comprehensive idea about those sensor terminologies, then you probably will not be aware of the parameters that we will be discussing in our upcoming sensor physics or circuits. Okay, till then, thank you.